Results of the study, the main result of this study is to be able to determine viscosity as a function of the concentration of fluorol SF14120. And when you can do that, you can determine what a simple solution is going to look like for different formulations. And a simple solution here is defined as a solution with only one non-Newtonian fluid. And so when you have a simple solution here, as shown over here, the flow curve is linear. And a linear trend line consists of two parameters, the slope and the y-intercept. And we don't like that because the slope might be a function of concentration. And so if you have two samples with different concentrations as shown on the right, two samples with different concentrations of the non-Newtonian fluid as shown on the right, then you might have a point of intersection if they don't have the same M value. And what that means is that those two samples now have the same viscosity for a particular shear rate, which is an inaccurate mathematical model because we rarely do expect to see that in reality. So what we would like is to be able to say that M is not a function of concentration. And to do that, we plot M values of samples created between 60% to 80% fluorol SF14120. And we notice that there isn't really a trend line when we plot it against concentration, that M values seem to randomly change, are randomly distributed around a mean of negative 0.71. So what that helps us to do is change our model from a two-parameter system and knock down the M parameter and set that as a constant, and now we're left with C. So we still aren't content because C is still not concentration. What we would really like is to be able to say viscosity as a function of shear rate and concentration. So let's see how C changes with different concentrations. So when we use the one-parameter system to find C values for samples of 2% fluorol SF14120 to 80% concentration fluorol SF14120, we see that there is a linear trend line, and that the samples are more accurate. The C value of the samples is more accurately measured at higher concentrations as compared to lower concentrations, but we expect that. But what we didn't expect is a linear trend line. So we can use this linear trend line, the equation of the linear trend line, and plug that into C, giving us the function of viscosity as a function of shear rate and concentration. However, X and Y, or the viscosity and the shear rate, are still in the logarithmic scale. So to be able to fix that, we do a little bit of algebra, and finally on the bottom in the red, we see the function of viscosity as a function of concentration and shear rate. We plug that in for different, we plug viscosity in for different concentrations and shear rate, and draw the figure on the right, and we were happy to find that there are no points of intersection. A second result of this study is to be able to anticipate the performance of a finish downstream. And so we focus on making a model of kiss roll wetting. And we find that if we know the flow properties of a finish through the previous mathematical model, we can plug that into this mathematical model along with certain information that we might receive from a customer, such as the RPM setting of a kiss roll and the diameter of a kiss roll, to figure out the shear rate experienced by the finish during the time of kiss roll wetting. So we can use that information to shortlist the formulations we test even further by, for example, in this case, we see that if the shear rate at which kiss roll wetting happens is at 50 hertz, then finish A and the old finish perform identically almost at that point as compared to finish B. However, if we had formulated finish A and finish B without having any information about their flow curves or the shear rate at which kiss roll wetting happens, then for a Brookfield viscometer, which typically measures lower shear rates, we might have recommended finish B based on it being closer to the old finish than finish A. As a final project in the rheology study, we asked the question, what would happen if we weren't dealing with a system that had only one non-Newtonian fluid? So when we did the study, we used fluorol SF14120, and then we also used particle dispersal of amide wax in PDMS fluid. And so we found that at low concentrations of the particle dispersals, we see that our predicted viscosity of the complex mixture is a good approximation. And it's an approximation because as we increase the concentration of the non-Newtonian fluids, we start to see that our prediction is underestimating the viscosity at any given shear rate for the complex mixture. And we believe that's because when we are in the simple solution phase, there's interactions between the non-Newtonian fluid and itself, along with the non-Newtonian fluid and the Newtonian fluid. However, when we're in a complex mixture state, there are interactions between the non-Newtonian fluids with the other non-Newtonian fluid, and the non-Newtonian fluid with itself, and the non-Newtonian fluid with the Newtonian fluid. So we expect to see an over-reporting, an under-reporting of viscosity, and when trying, so if there is, if we choose to do future work where we aren't content with a good approximation, and all we would have to do is we would have to change the prediction equation, which we are currently using is a simple addition of the viscosity contributions in their simple solution state, and then we would have to make it something more complex that accounts for the interactions between wax and max stirred particles.